didn't know it at the time, but the case of this common weed would be uncommonly tough to crack. The subject of our mystery was a plant of two phenotypes, one a wild type, the other a mutant. You would see the differences even at the macro level. The mutant seemed to display an unusual array of root hairs. It was for this reason that my lab brought him in for questioning. This mutant was a triple knockout, lacking the XI1, XI2, and XIK myosin genes. Myosin motors are an important component of the actin network. They provide motility to a vast array of organelles, including the endoplasmic reticulum, Golgi, and peroxisomes. As my partner and I scanned through our first set of clues, we confirmed exactly what our sources claimed to be true. While the wild type's root hairs were long and generally straight, the mutants were bent and contorted, shortened because they lacked the myosin genes that are important for rapid polarized growth. It has also been shown that mutations in the XI2 and XIK myosin genes cause reduced velocity in the movement of Golgi, peroxisomes, and mitochondria. So my partner and I went on the hunt for some more evidence. Our search began with the bright field microscope. While we were able to see some streaming, we knew these weren't the results that we were looking for. So we took a closer look with the confocal microscope. Bingo! We were finally getting somewhere. We could see the root hairs much more clearly and get a glimpse of just what was going on. And there seemed to be much more going on in the wild type than the mutant, backing up previous information. But we needed to know more. How did this mutation affect the movement of organelles? To further our investigation, we decided to shed some light, UV light that is, on the endoplasmic reticulum. The thing is, though, we hit another wall. We could see some ER localization, but not enough. For the wild type, the solution came through a new protein, YFP, instead of CFP, and for both, it would be back to the confocal. We could finally see the endoplasmic reticulum, and the differences were clear as day. The mutant was disconnected and less active than the streaming wild type. As a final test, however, my partner and I decided to see how the subject reacted to stress. We zapped portions of the ER with a 488 nanometer laser and watched how it recovered using FRAP analysis and particle tracking. What followed was a flurry of data and analysis. The pieces, we just had to put them together. And under close examination, some trends began to make themselves clear. The wild type tended to accumulate more ER to the sites of the photobleaching than the wild type did, and this was consistent with the idea that the mutant type has a reduced velocity. Taking a look at the velocity graphs, however, it's tough to get a clear picture. There's a slight trend with the wild type speeding up during the recovery period, but there's too much deviation and not enough consistency to be sure. All we know is that there is more to this case than we first thought. So can we call it closed? I don't think so, and that's just the way it is in this scientific world.